Okay, hi everybody. I'm glad that you can make it to this webinar this evening in UK time, but morning California time. It's a pleasure to have Yan Liu here from Google, who's giving up his time to discuss all his expertise in the field of healthcare, specifically related to machine learning across the medical spectrum. He's done an immense amount of research in this field, so giving up his time is always, a positive. So very happy that you could join us here for our Clinician Engineer webinar evening, and happy to hear your presentation, sir.
Thank you, Neil, so much for the invitation, and welcome to all the attendees. Really glad to be here. Let me share my screen and just make sure that that's working okay. Is that coming through?
Perfect. Yes, you can see us.
All right. So today I'm going to give a bit of a brief talk covering multiple areas that we are working on. And really the objective here is to give you a flavor of the kinds of stuff that we do research on, and to really, open the floor for discussions and any questions that you might have. So the kinds of work that we do really revolve around artificial intelligence in the healthcare space. And turn on the pointer. And so the terms that you hear related to this also include machine learning and deep learning. And really, they are very much overlapping. And so machine learning is really a way to get machines to learn from data. And deep learning is a kind or a category of machine learning techniques. And AI is kind of a slightly less well-defined term, but it's meant to indicate that we're trying to develop things that can perform tasks that traditionally you might expect requires intelligence. Now, deep learning and machine learning are all around us, and it's used in many products. And so here are some examples from applications from Google. And so in this case, for example, for Google Photos, if you were to search for a phrase here, so in text, it will try to pull up things that it thinks matches that text that you search for. And this is without you having to go back to each photo and tag them with what's in those photos. And this is done actually via machine interpretation of what's in those photographs. Similarly for Gmail, if you're working on Gmail, what you might see is that there might be suggested responses to emails. And what that can help you do is really to accelerate your ability to respond to emails quickly. And the way this is done is really by a machine looking at the emails and trying to understand what it's saying, and then predicting what are some potential responses that may be valid for that particular email. Translate is another one, which is based on language understanding via machine learning. And so Google Translate really does make use of the fact that machines need to be able to understand what that language is saying beyond just dictionary-based replacement of words. So in terms of machine learning and AI in healthcare, the interest in that has really grown over the past years. And so there's been a huge increase in the number of papers that's published in this space over recent years. And in this talk, what I will try to do is to give you a sense of two categories of work that we engage in. The first category are to use AI to try and do things that doctors already can do. And what this is helpful for usually is to really help improve access to healthcare by really enabling this expertise to be shared around the world, particularly for places that may not have that expertise readily available. The second category of work are to do things that doctors can't do right now or don't know how to do quite yet. And I'll talk about what that means later on in this talk. So in terms of the first category, one of the first examples that we really engaged in was to tackle diabetes more generally. And so that
Hello, Yan. Can you hear us okay?
really impact many areas of the human body. One of the areas where it can have this effect is in the eyes. And what it can do is to really cause the blood vessels in the eye to become leaky. And as fluid comes out, it starts to damage the eye and also affect the vision. So what we see here on the right is a picture of the retina of the eye, and it's taken by a machine like the one you see on this left side. And this is a healthy eye. And so what you see here is that there's this optic nerve, that's the That's the white bright part here. Here's the central vision, the fovea, and you see blood vessels all across. When these things start leaking, it can really damage this retina. So I'll show you an example here on the right, which is one with many hemorrhages over here. And so these are indications that diabetes has started to really affect the eye. Now, this disease called diabetic retinopathy is graded on a 5-point scale, ranging from none all the way to proliferative DR. This particular grading scale is well known. And if you have screeners and graders around to actually take the photos and grade those photos, you can actually do a pretty reasonable job of catching these things fairly early on, perhaps when it's in the milder stages. And what you can do is try to help the patients control their diabetes a lot better and hope that this disease actually resolves. Now, the problem is that in many areas of the world, there actually aren't enough eye doctors to do the screening and to then to do the screening, grade the images, and then manage the patients. And so many patients actually do not get to see an eye doctor in time in order to preserve their vision. So what we did in this early work was to see if we can create a machine learning model that can help grade these images. So given an input, find this image, predict what is the grade supposed to be. And the way that it's done in machine learning is really to show many examples of the image in question, as well as the desired output. So what we did was to produce a labeling tool and worked with many ophthalmologists to grade over 100,000 images and many grades for these same images. And the number of grades exceeds the number of images because we got multiple grades per image. Now I'll talk about why in just a second. The bottom here is an illustration of this machine learning model. It looks complicated, but what's really happening here is that the input comes in, the image comes in on the left, and there are layers of different kinds of computation that happens to process the image before at the very end, it produces the output prediction. So this is why we need many labels per image. This is a very colorful chart. What is indicated here is every row here is one image. And then every column here is one grader. So every image got graded by multiple graders, and every grader graded multiple images. What we would like to see, and the ideal situation, is that you see horizontal bands of colors, and that indicates that each image got exactly the same grade from every single grader. And we do certainly see that for a few images. So the bottom two rows, for example, is a pure sort of like proliferative grade assigned. But we don't see that for every image. In fact, here are two examples where this image in particular actually got at least one grader grading it for every single one of those 5 grades. And so generally what we call this is that every time you have any amount of subjectivity in a grading system, and most grading systems do have some amount of subjectivity, we do see a problem with inter-rater variability. And when you have variability, the question comes, the question arises as to what is the right ground truth for this image? Is it grade 1, 2, 3, 4, or 5? And to help resolve that, what's really helpful is to really get multiple grades per image, get more experienced graders, and then figuring out how to adjudicate those differences. So adjudication is really a process where we get experienced graders who disagreed on a particular image to come together, sit down, and then discuss the differences and figure out what the grade actually was supposed to be. And when they do these discussions, sometimes they find, oh, actually, I didn't see that thing that you were referring to, or they might discuss and come to a different conclusion about how they interpret something that they did indeed see. So what happens during adjudication really is that the quality essentially of that ground truth that we use to both train and evaluate the machine learning model gets better and better as you do these adjudications. So what happened over time, and so this is a sort of like performance plot of our model from back in 2016 versus a more recent model back then in 2018. And the model actually improved its performance from being on par with general ophthalmologists to being more on par with specialists or retina specialists in this case. And really what changed there, the biggest thing that changed there was really the quality of the ground truth that was used for training these images. So the takeaway on this slide really is if there's subjectivity in the grading system, really do make sure that the ground truth you're using to train and evaluate the machine learning model is really high quality, because otherwise you're not really measuring what you think you're measuring. So as a follow-up to this work, what we then did was say, well, we don't want to stop at a model. We do want to see if we can use this to help people. So here is one example where we're working with the within the Thai national screening program with a few hospitals there. And this is an interface, and this is all in Thai, but this is an interface where the nurses and technicians who are taking the photographs were able to upload those to a web interface. And in this case, it's just two sort of like centered images, left and right. And what the model returns in a few seconds is its interpretation of that image, whether in this case, whether there was DR and whether there was DME, two different forms of diabetic retinopathy. In this particular case, the screening program also uses the visual acuity as part of the screening process. And so these are entered by the nurses. In addition to Thailand, we're working in India to help improve this, because part of this work was also started with collaborators in India. So I'm going to shift gears just a little bit right now to talk about a different application where we've worked on using machine learning. So here, instead of working on diabetes, this deals with breast cancer. So in this case, what we're working on here is really to figure out if a breast cancer is spread away from its primary site into the lymph nodes. And usually the way that this is done is actually by pathologists who take out cells from the body and look through those cells under a microscope to see if there's any tumor cells. So here's one example of such a slide. So what has happened is that this tumor has been taken out. Well, actually, in this case, this is a lymph node. This lymph node has been taken out of the body. It's been fixed, cut into slices, and stained with special chemicals to enhance the contrast of the cells. And so what you're seeing here on this slide is actually only about 1 centimeter across physically on a glass slide. When you do zoom in to very high magnification, say 400 or 500 times magnification, what you can then see are these cells that are sort of like really small on this original slide. Now, tumor can be seen in these slides. And so on the right here is one example where you see, actually in this case in the stroma, like some very scattered tumor cells within this. Now, what's striking here is that tumor to the untrained eye is actually quite similar to some benign mimics, so-called, of tumor. And so it's actually not a trivial task to find tumor in here, because you really have to look at this fairly carefully, usually first at a lower moderate magnification and then zooming in whenever there's something you're unsure about. So this can be really laborious for pathologists who are doing this task. The way that we approach this problem from the machine learning perspective was to say, well, let's take the high resolution image of this microscopy slide. Let's tile it and create a grid out of it. And for each tile, let's ask the machine to look at it and determine whether that's cancer, yes or no. And part of the reason this is done is because this image is so large that it doesn't really fit in most computers' memories. So you can't really just work on it right off in most cases. So in addition to tiling the original image, what's also fed in is actually an annotation of where the tumor is on each slide. So in this case, red indicates tumor, blue indicates not tumor. And so in this case, this particular slide has a fairly large macrometastasis here that is very, very apparent even at low magnification. And so, the annotation maps here are quite clear. Now, when we train the model using these examples, it can then gradually learn to recognize what is tumor and what is not tumor. So here are two examples of what came out of that work. Left to right, the leftmost column here is the same kind of like microscopy slide at low magnification. The middle column here is the ground truth, where red represents areas where pathologists indicated that there was tumor. So the top one is a very large tumor. The bottom one is a small tumor right here near the bottom of the slide. Now let's look at what the model thought this was. So the model obviously creates sort of like more of a continuous scoring. And so it doesn't just provide 1 or 0, but also colors in between. And so this is what that color bar represents. The model was very certain that there was a very large tumor within this particular slide, and that matches up very well with the annotated ground truth. What is interesting here, though, is that there are some spots right here in the middle that was not in the annotation, but the model highlighted. And it turns out that these smaller areas actually were tumor. It just was not annotated in the original slide. So this highlights one area where models can really make a difference, which is much more exhaustive. It is not getting tired. It can do things that humans are not meant to be able to do. To be fair, this is actually not a very clinically significant thing, because if there's a very large tumor over here, you don't really care if there's a small one there. But if this was the only tumor that was on the slide, then that would have been quite significant. In the bottom example, similarly, we see that the model identified some of the tumor right at the bottom, but also notice that it has some areas that it's slightly more uncertain about. And so what is helpful here is that when the model highlights something like this, people can then look at it and see if that is indeed tumor or not. So it can really help accelerate their review of a slide. So this is a summary of the technical evaluation, and the details here aren't particularly important, but what we should focus on here is the fact that the model, so the x-axis here is the number of false positives per slide, that the number of predictions essentially that the model is making. And as you allow the model to make more predictions and potentially get more things wrong, what will happen is they'll also get more things correct. So there's a trade-off between how stringent you want it to be and how sensitive it might be. The advantage there is this green dot here represents pathologists, and they're not making any false calls. They understand tumor when it's there, and they can indicate where the tumor are. The model is actually, when you're not allowing it to make any mistakes, it's actually not as good. However, once you allow the model to say, hey, here's a couple of things I think might be tumor, its sensitivity increases quite a bit. So really here, the strength here is that how do we combine the ability of humans to really look at something and from experience really understand what it is with the ability of a model to exhaustively scan a really, really large image. And that's exactly what we set out to study next. So all we did here was we really say, hey, let's take a bunch of slides, let's run the model on it, take its predictions, and then provide those predictions, essentially pointers of where the model has thought there was tumor, and provide that to human pathologists to go look at. And when we did that, and we stratified the cases by 3 categories. 1, N, meaning it's negative, there's no metastasis there at all. Second category is micromets, so very small tumors. Third category is macromets, so larger tumors. And we wanted to understand how fast does it make them? Does it actually help them improve their efficiency at all in any way? Here's what we found. For very, very large metastases, so very large tumors, many of whom are actually visible, almost by the naked eye, if you just put up the slide to the light, the differences in time were very minor. They're all under a minute. So, not a huge difference. Promisingly, here's what we expect to see, which is for smaller metastases, there was a huge difference in the amount of time it took to look for metastases on slide. So without assistance, it was about 2 minutes. With assistance, about 1 minute. So that's a huge difference. It's like a 50% reduction in time taken. What we didn't quite expect, but that we were encouraged by, was for negative cases. Pathologists were searching for upwards of 2 minutes without the AI, but with the AI, they were comfortable searching for slightly less time. So what this is indicating is that they were comfortable trusting the AI after using it for a while, that they were comfortable stopping their search after a certain point in time. So we were pleasantly surprised that this was actually happening as well. Now, in addition to efficiency, we also want to make sure that they were not just getting faster, but they were just as accurate as they were previously, because if they started missing things, it wouldn't really matter if they were any faster. And what we saw here, so similarly the 3 categories, negative, small tumors, larger tumors. For larger tumors, really no difference. And this is something that one might expect because it's so large that you might have been able to see it irrespective of any kind of AI assistance. And for smaller metastasis, what's interesting is that the accuracy improved quite a bit, from below 85% to upwards of 90% once they had AI assistance. And this was really because it allowed them to very rapidly hone in on the things that they should be looking at. So not only were they faster, like only at twice the speed, they were also more accurate for small metastases. For negative examples, this was quite reassuring. This did not cause them to be any less specific or to overcall tumors in any situation. So this was all quite promising data. So then one other thing that we tried here was, hey, can we, all of these technologies that we're building for cancer pathology really requires a really high resolution scan of each image. And those high resolution scans, the machines used to capture those scans can cost upwards of 200,000 in certain cases. And is there a way we can build this into the average pathologist workflow a little bit better? And for many years, pathologists are using microscopes to do their reviews of cancer slides. And what we've done here is to say, hey, really a microscope is doing the same thing that a scanner is doing, just one field of view at one time. So what was happening here is that a live video feed was capturing what was seen in this image It was sending it off to the computer via this cable. And the computer was running the AI in real time, and then in real time feeding that back into the field of view of the microscope. And so what we see here is on the right, where someone is scanning the slide, moving around. And then once it hits a tumor, within half a second or so, there's a highlight that says, hey, look, there's something here. This was more of a proof of concept work, but what it really showed was that it's actually feasible to A, build this in and have the AI actually run all of this compute in essentially real time. And B, that the models that we have been developing, at least in certain cases, generalize to images taken in this particular way, because there are differences in the optics and so forth between a large scanner and the microscope. Here are some more examples of what we just saw, where there's outlines across different tumors. And what's interesting here is that we were able to create models that work at different resolutions. And we showed that with different sort of like microscope objectives, we were still able to get the model to be working at many of these. All right, so that concludes sort of like the first part of the talk, covering just a couple of areas where we were working on things and really using machine learning to do tasks that doctors are expected to do day to day right now. The next part of the talk deals with things that doctors cannot do right now. And what this means are things like disease prognosis and other kinds of predictions that we don't necessarily know how to do right now, but we can potentially ask the machine to learn and to see if it can do a better task than our current knowledge serves. So here's one example, and this deals again with the diabetic eye disease situation. Now, on the left here, these orange photographs are what we saw earlier. So those are retinal fundus photographs. So these are 2D color photographs of the surface of the retina. And so it gives you fairly limited information about what's going on deeper in the retina in the different layers. Now, in clinical work, what is usually done if you want to visualize what's happening beneath the surface layers is to use a technique called OCT. And this is an optical technique as well. But what it does is that it focuses on a very small section of the retina, and it gives you a 3D sort of like view of what's going on in those layers. What happens though is that for some diseases, diabetic macular edema, for example, it really results in fluid and other things accumulating within different layers of the retina. And that's very much visible in the OCT 3D scan. It is not as readily visible in the fundus photograph. Now, there are proxy measures, for example, hard exudates and other things that you can see in the 2D photographs, but those are not always visible not always accurately visible until you get to 3D imaging. What that means, though, is that the cheaper 2D visualization technique doesn't necessarily capture the things that you see when you use the more expensive technique. So patients often, when they're undergoing screening, and that screening is done by this 2D imaging, and then by the time they get to the eye specialist, they get another scan, they go like, oh, actually, that wasn't as bad as we thought. You're okay. And that's a good outcome from the screening perspective. But what it can result in is a lot of resources that are used to screen people who you otherwise might not have needed to come in at all in the first place. Like if you are in principle able to do this 3D sort of like more expensive imaging for everyone to begin with. So the question we asked was, hey, can we use machine learning to take as input the 2D image? And is it able to maybe look at the pixels with enough granularity and extract information we couldn't extract ourselves and understand if they would have been candidates for treatment later on using a 3D imaging? And that's what we did here. The blue line here is the model. And what you can see is it is much higher than the 3 dots over here. The 3 dots are, in this case, retina specialists looking at the 2D image and looking out for those hard exudates, so those proxy measures of DME in the 2D image. The ground truth here is coming from the 3D OCT scan. But I should emphasize that neither these doctors nor the model had access to the 3D scan. What they all saw was a 2D scan. And so what this proof of concept really showed was really the ability for machine learning to really help detect things that's not readily apparent to the human eye, or that current grading skills aren't perfectly capturing quite yet. And so this is just a capture of the similar result and just really zooming into what OCT and 2D retinal imaging is showing. within a very similar framework, we also did a different kind of work, which is instead of saying what would have happened if we took a 3D image of this eyeball right now, we asked a different question, which is what will happen to this eye in the future? And what that means is, in this case, these are all patients with age-related macular degeneration. And the question was, what will happen to this patient after 1 year? Now, from a human perspective, if there are things that we are taught to look for in the eye, we can try and grade for that, and that gives us a sense of the prognosis of that patient. However, from a machine perspective, what we can do is to say retrospectively, let's take a number of cases where we know what the image looked like at t0, so at a present time. And because it's a retrospective study, we can actually provide it what would have happened in 1 year's time. And so we provide that as a label to the machine learning algorithm. And what it's able to do is to look for signs itself of what correlates between poor prognosis later on and the current image. What are the signs in the current image that we should look at? What we showed is that there are different grading scales here, but what we showed is that the model actually was able to extract more signal out of these 2D images to try and do prognosis. And a natural next step is, can we leverage this to understand better the disease pathology process and really to improve our ability also as humans to be able to do this task. And some of their work is ongoing. Here's yet another example. So in this third example, we're also working with 2D retinal photographs. But what we're doing is to say, hey, retinal photos are actually fairly unique in terms of medical imaging. And it's unique from the perspective that this is a very non-invasive way, because it's just a camera that's pointed at the eye. And it's a non-invasive way of imaging the microvasculature that's in the body. And that's something that we don't usually get with other ways of imaging. So the question is, do these vessels and other things that we're seeing here, and nerves as well, do they give us any information about cardiovascular risk, about other things that's going on in the body? And so in this work, what we did was to say, hey, there's a number of cardiovascular risk factors, age, sex, A1C is a marker for diabetes, and blood pressure. Can we predict some of these things from retinal photographs? And this is more of a proof of concept, because age you would not try to do from retinal photo, you would ask the patient. And what we showed was that actually this was shockingly high in terms of how well it could predict age. And this was 2 to 3 years on average for age, and with an AUC of 0.97, so near perfect for self-reported sex. What was surprising here really was that for age, there were some signs that people could actually tell whether it's an image of a young retina or older one. And mostly that's because younger retinas have a sort of like a sheen of youth, which really results from one of the layers being just a little bit different. But no human has been taught or know how to determine the precise age of the image that they're looking at. The sex was an interesting one. There have been prior reports that certain parts of the optic disc, and other parts of the retina might look just a little bit different between the sexes. But to really be able to use the information to do accurate identification was not known previously. So in addition to these risk factors, some of which were more demographics and some are potentially modifiable, we looked at whether this could be used to directly predict the 5-year major adverse cardiac outcome. And on the UK Biobank data, which this was done on, we saw a preliminary result of about 0.7 AUC. So that is fairly respectable. I should say that a lot of this predictive information does come from some of these risk factors. So not necessarily that we are currently, that was clear in this work that there was additional information there, but this was really promising as initial proof of concept. So that's work on cardiovascular risk. Here's another example. Apology for the blurriness, but what we see here is we were using the same retinal photographs, and instead of asking it to predict outcomes in the future or to predict what you would see in different kind of imaging or different age and sex and other things, we're asking, what if we took the closest blood test that we have for this corresponding case, and in the blood test we're able to get their hemoglobin levels as well, and from their anemia status. Can we ask the machine learning model to predict the hemoglobin levels from the image itself? And there's some background to this, where we know that if someone has really severe anemia, there are different parts of the body, if you put on the eye and look at it, where it all just gets a little bit paler. So there's some evidence that one can potentially see signs of severe anemia, but there wasn't known that one can maybe do this with any amount of accuracy. So what we did here was to say, okay, let's try and do that, but we need a baseline. If we don't have a baseline, we don't know if it's just doing this because the model is able to identify age and sex from these models. And we do know that for hemoglobin levels, for example, the sex of the patient is actually very, there's a correlation between sex and hemoglobin levels. And so that correlation would have been sufficient if that's all the model was identified. So what we did was to say, okay, let's have a model that we train using metadata, so age, sex, and a few other variables. Use that to predict hemoglobin and see how that does. So that's what we did here. And what we see here is 2 clouds of points. This is the actual concentration here on the right side. Then the top axis here is the predicted concentration. We see 2 clouds, and these are essentially clouds of points representing male and female patients. And so this, the error here was 0.7. Now, when we did it from just the image, we saw that there's no longer 2 cloud of points. So it wasn't doing this just solely based off being, male or female. Instead, what we saw was a fairly long continuous cloud of points, and the error there was 0.67, so a little bit better than what this was showing. And then what we finally did was to say, let's combine this information, right? So that's in addition to saying, hey, can the model extract information from the fundus photograph? Can we tell the model also at the same time, this is the age and this is the sex of the patient, and have the model sort of like calibrate its expectations appropriately and output a prediction? And when we did that, we sort of got the best of both worlds, and we got the error down even further to about 0.6. So this was all very promising data, and we did quite a bit of careful explainability work here to show where the information was coming from in this work. And that concludes the tour of the kinds of work that we have done in this area. There is a link below here to our Google Scholar page, which links exhaustively all of the papers we've published in the AI for healthcare space. With that, I am happy to take any questions.
Fantastic, thanks so much. Very comprehensive. I do have some questions for you if you have time. So there is always the debate about AI and HI, human intelligence. And clearly, doctors definitely miss things. For example, if I draw a parallel to digestive diseases, we do a lot of endoscopy. We may miss polyps or early cancer, and artificial intelligence has come in that space. You've probably been asked this before, but maybe I'll ask it you. Do you think AI would completely replace doctors in the future, or do you think both are needed side by side?
Yeah, it's definitely a great question, and one that's been asked quite a bit. I would say that I would say that AI is a tool, just like any tool that that doctors might be using. And so what's really important here is to really figure out how we can combine the best of both worlds. And just like, we acknowledge that humans aren't perfect, we may make mistakes as humans, as people, right? AI isn't perfect either. And really, how do we combine these two? How do we, go from AI to for artificial intelligence to augmented intelligence, where people and AI are able to work together effectively to deliver the best care possible to patients? And really, that patient-oriented approach is the way I would approach and think about it.
Yeah, no, I agree with you. Another parallel, I know that in the healthcare space, organizations are using AI in the sense where symptoms are put into a device, and then the AI algorithm would say, okay, you have X, Y, and Z, and potentially you're having a heart attack, or potentially you're having a stroke. So I think there's a lot of potential, and definitely because you're based at Google, the accuracy and the quality of your work is top dollar, as they say. For us as the clinician engineer hybrids, because we know that in healthcare and in medicine, engineering is surrounding us, but we are trying to now understand it more. When you look at the AI algorithm and the basic concept of input, hidden, and output, are you able to explain for clinicians out there that don't know much about AI, what is actually going on in that hidden space? Or is it still kind of unknown?
Yeah, that's a great question. So explainable AI is a large and growing field where people are trying to answer exactly that. And there's been a lot of great progress. And a lot of open questions remain unanswered. Maybe a bit of a, so let me go back to the slide where I showed one of these AI algos. 1 second. So over here.
Yeah,
so some of this, so some of this looks a little bit intimidating just because of how many things is going on within this chart.
Yes.
But really what's happening here is that the model is trying to process the image in layers of compute. And at the high level, the inspiration for this is how the human neurocortex is working to get human vision from the eyeballs all the way into sort of like higher level processing. And so when we examine what is happening in these networks, usually what is happening is that the first few layers tend to be doing something that are more primitive. So it might be saying, where are the edges within this picture? Where are the dots? Where are these other little things? The middle layers tend to be doing something slightly more higher level by saying, let's combine those features that we saw, the lower layers, and look for slightly higher level features, like where are the microaneurysms? Where are these borders of these other lesions that we're looking at? The very highest levels tends to be then combining those middle level features into higher level concepts. And the very last layer over here tends to be then pulling all of that information together and saying, hey, what is this actually? And what's remarkable really is the fact that, from the earliest layers to the latest layers, all of this, when the model is learning, starts from scratch in terms of there's no information available. But in the process of showing it many of these examples, it gradually learns to identify a pathway and a set of features that it thinks is really predictive of the task that it was told to go learn how to do. So I think that's the high level sense of how the model is working. I'll add one more thing here. In terms of explainable AI, what we can also do are experiments where we essentially cover up different parts of the image and then ask it like, hey, if we cover this up, how does your prediction change? And when we do that, we can interrogate and understand which parts of the image is most important to this model and its prediction. There are also other ways of saying, okay, let's trace back the pathway of a prediction and say, where does it start from essentially in this image? It gets really complicated because this is not one linear sort of like computation pathway, but we do often see many heat maps in the literature where it's highlighting different parts of the image that appear to be important for each prediction. And those are all things that can really help us, guide us in our understanding of what the model is doing. Both from the perspective of how is the model working generally and what is causing this model right now for this given case to produce this given prediction, right? So there's two kinds of understandings that we're really trying to strive for, but both are really important. So great question.
And I think that was an outstanding answer. So yeah, thank you so much, because definitely as clinicians and scientists looking in this area of AI and trying to understand it, you explained it brilliantly. Just a follow-up question to that. So then as we get excited by AI, do you have any courses or training that you could recommend, like basic ones that would be exciting to be part of? Or do you think clinicians should just focus on the clinical work and then collaborate with engineers and leave all that to them?
Yeah, so I think definitely, everyone should understand enough pieces so that they are comfortable with what is happening. So I would say, similar to say MRI machine, I don't think we expect the end users of MRI when you're reading the scan to be really like, I am empowered to fix the MRI machine if it breaks. Like, I don't think anyone is able to do that. It's similar to when we drive a car. Most of us don't know how to fix the car, but we roughly know it's a combustion engine. We're putting in, say gasoline, and it's burning something. There's some things that are turning and makes it move. So there's some level of, I think, baseline understanding that's really helpful for us as users. But we don't need to have the full end-to-end system understanding, because that's rarely the case for anything that we use in any case. So I think there are some things definitely that are useful here. There's a number of review articles and other things that are useful for physicians. I'll point to one that we published in JAMA a while back. I'll open it right here. This is all within that Google Scholar profile that I pointed to earlier. And so this is the in their users guide series. So JAMA has a series where they try to provide articles that provide sort of like a clinician accessible way of really understanding a topic to the extent that they need to understand to do their work. And so some of it deals with statistics and how do a statistical test do, how do you interpret a diagnostic test, what is sensitivity, specificity, that sort of thing. But there's a 2019 article on how do you look at articles that use machine learning, and what do you really need to know about machine learning, and what it actually is doing.
Fantastic. This is all very, very useful information. Yes, absolutely. And the final question, if you have a moment, the data side of things. Often people say access to data may be tricky, but with ethics, etc., that's okay. I guess from my perspective, how much data is really needed to get a good outcome models wise? I find that people say different things, and then there's also this concept of maybe synthetic data. And as a basic clinician with basic engineering knowledge, it'd be good to know how much data are you inputting in the system?
Yeah, that's a great question. I think the short answer is nobody really knows, right? The more subtle answer is that this is improving with time as we have more advanced techniques and better ways to leverage the same kinds of data. And as we understand the problem space itself better, often we can reduce the amount of data required. Here's one specific case of one of our earlier work. And so in this case, this was the data set size. The full data set, training data set, was 100,000. Right. And as we had more and more data, the accuracy of the model got better and better and better. But at some point, it starts to plateau a little bit. Now, I should clarify this was one of our earlier data sets. And so what actually happened here is that this was before we did all of the adjudication, where we got some of the grading uncertainty resolved. We were just using majority of multiple graders back then. But once we got things adjudicated, what actually happened was that the model was able to be much more accurate. And so it actually went above this area where it plateaued in this particular study. One other thing to point out, when we do machine learning, there are multiple data sets that we use, even in the development phase alone. So it's not as the case that we provide one single data set, the machine sort of like, takes in that entire data set and it spits out a model. There's actually usually very typically two sub data sets that's used. One is a data set that the machine learning model is actually actively training from, meaning it's seeing those examples and then it's making a prediction, and if it gets it wrong, it gets a signal that says this was wrong and this was how you were getting it wrong. So change your internal connections to make that to avoid making that mistake. And the second data set is what we call a validation or a tuning data set. That second data set is actually used to tune several things about how the machine learning model is working. And that's actually to do with the way that it's trained, where when it's training, there's something called a learning rate, which is how quickly do you want it to correct its mistakes? Because if you correct it too quickly, it goes like, oh, wait, this is completely wrong, and doesn't know what to do sort of like next. But if you do it too slowly, then the whole process just takes too long, right? So that's one example of a setting that needs to be tuned during the learning process. And so this tuning data set size is actually a second thing that's actually quite important. And our experiments actually found that the size and the quality of the tuning data set is actually really, really important. And the reason is because that tuning data set gives you a sense of how you are doing on examples that the model isn't directly learning from, right? So it gives you sort of like an independent signal. So outside of the size of the training data set, we do need to make sure that the size and quality of the tuning data set is actually quite good. So fairly long-winded answer, apologies, but there's multiple data sets in here. The size and quality of them are all quite important. The amount of data that's needed over time is slowly improving and decreasing with time because we get better techniques. But end of the day, yes, you do need some amount of data to do machine learning.
Brilliant. Another great explanation. Thanks so much. Well, thanks for your time. I know that you're very busy over at California and the Google base. I'm sure you've got lots of exciting projects ahead. We really appreciate the time that you've given, and we'll close the session then. So for anyone that is not able to attend, our video will be available on our YouTube channel. And thanks again to Jan, and we'll stay in touch. Take care. All the best.
Thanks so much.
Bye.